In this video, I'll be talking about pumping lemma don'ts, focusing on cases. Now, the reason that we have to have cases when we use the pumping lemma is because one of the incredibly important steps of the pumping lemma is demonstrating that no matter how we break our word up into its relevant segments, and those relevant segments actually differ depending on whether we're talking about the pumping lemma for regular languages, in which case we're dealing with X, Y, and Z, or whether we're dealing with the pumping lemma for context-free languages, in which case we're dealing with the double pumping lemma, and that is U, V, X, Y, Z. So part of the pumping lemma proof is demonstrating that once you've picked your word, there is no way to break that word up into its relevant segments such that we can pump the bits that should be able to be pumped. So we should, in theory, be able to pump the Y in the regular language pumping lemma and pump the Y, the V and the Y in the context-free language pumping lemma. So let's understand what's going on using an example. I'm going to define a nice simple language that I'm going to call increasing. So this is sequences of increasing numbers represented in unary. Now, this isn't strictly increasing, so we can have numbers that are the same, but our numbers do have to be either equal to or greater than the previous number. So for instance, let's just say we want to communicate 3, 5, 6. Now, we want to write this in unary, and let's make it that each number is separated using a dash. That seems reasonable. So this represented as a word in increasing would be 111 dash 11111 dash 1 2 3 4 5 6. So this here is a word in increasing. It's really important when you pick your words that you do actually make sure that you pick your words such that they are in your language. Now, the only problem with picking this word for a pumping proof is that we're not actually ensuring that it's long enough. So if we were doing a regular pumping proof, we would have to make sure that the length of our word was greater or equal than n, where n is the number of states in our theoretical FA. And if we were doing a double pumping proof, we would have to make sure that the length of our word was greater or equal to 2 to the k take 1, where k is equal to the number of non-terminals in the Chomsky normal form representation of the grammar of our language. So a really common thing to do if you're dealing with a double pumping lemma proof is to actually say something like, let 2 to the k equal n, and then proceed as though you're in a regular pumping proof as far as defining your word is concerned. So because this isn't about picking words, this is actually about how you find cases once you've picked your word, I'm actually going to cut ahead. I'm going to cut to the chase and skip ahead. And I'm going to write out the word that I intend to use. So I'm going to say my word is equal to 1 to the n dash 1 to the n plus 1 dash 1 to the n plus 2. We can see that this is indeed a strictly increasing sequence, which is not actually necessary. This is actually just it is a strictly increasing sequence, which means that it is part of the language increasing, but the fact that it's strictly increasing isn't actually strictly necessary. Yes, I'll just leave a pause there so you can all groan. Now, we haven't actually decided, are we doing a single pumping proof or a double pumping proof? So let's talk about how we might pick our cases in either of those scenarios. In a pumping proof for a regular language, we have 3 restrictions for how we go about picking our X, Y, and Z. And those restrictions are our word must equal XYZ, our Y cannot be empty, and the length of XY must be less than or equal to n. Now, it's this final rule that saves our bacon over and over and over again, because the fact that our XY must be less than or equal to n means that, given this word over here, I can't actually let my XY go further than this point in my word. So that's going to restrict the number of cases I have to consider. And it turns out that I can actually just say, well, my Y has to be non-empty, and my Y can only be found in this group of ones. And, well, this group of ones only contains ones. So how about we say my Y must contain ones from my first number. And that's my case. So this is actually a really good case. And it turns out that I don't need any more cases in my proof. But I said at the beginning of this video that this was going to be an example of things not to do. So how about let's look at how we might muck this up. Now, a classic way of mucking this up is to say something like, let Y equal 1. And, let X equal the empty string and Z equal 1 to the n minus 1 dash 1 to the n plus 1 dash 1 to the n plus 2. This is a classic mistake that I see all the time. The reason that it happens, I think, is because the logic that's going to be used is identical between these two descriptions. In both of these cases, you're going to end up saying something along the lines of, well, if I is equal to, let's say, 3, so when I equals 3, my first number will be bigger than my second number. I'm not going to bother writing that out. So that logic is the same between both of them. And so oftentimes I see people writing pumping lemmas, and because they want to be very precise, they want to be very mathematical, they want to make sure there's no hand waving going on in their proof, they specify their cases to this degree of specificity. The only problem with this is that this is not all possible ways that my word can be broken up into X, Y, and Z following these rules. There are lots of ways. There are actually, because we don't know what the number n is, there are an uncountable number of ways that we can break our word up into X, Y, and Z. So we need to be really, really careful that the cases that we provide are sufficiently general that all possible ways are covered. Now let's get rid of this red. This red is unnecessary. And focus on the green, because the green is good. And looking at that green, we can actually see that we've covered all possible ways of breaking this word up into X, Y, and Z. So let's move on from the regular pumping lemma and let's have a look at the double pumping lemma. Because the double pumping lemma is, I'm not going to be able to erase that, am I? Well, let's just rewrite that dash. The double pumping lemma is actually going to be a lot more interesting. So, the rules for the double pumping lemma are, get rid of all that. The rules for the double pumping lemma are, number 1, our word must equal u, v, x, y, z. So in the double pumping lemma, we're breaking our words up into UV, X, Y, Z. And our Y and V together cannot be empty. So note that this means that our V on its own could be empty, our Y on its own could be empty, but both of them at the same time cannot be empty. And then finally, the length of Vxy must be less than or equal to 2 to the k. Now, if we remember up here, we said something like let 2 to the k equal n. So you can sort of see how our word should map onto our third rule. Now, the major difference between the regular pumping lemma and the double pumping lemma is this third rule. So, yeah, you've got more letters to play with. Yes, there's like 2 things that can't both be empty rather than just the one thing that can't be empty. But the thing that makes double pumping lemmas difficult is this third rule. Because notice that this third rule begins partway into our list of letters. So with the regular pumping lemma, our third rule started at the start. It started with the X. So it meant that the part of the word that gets pumped was tethered to the start of our word. Whereas here, we've got this free-floating U. And this U can be whatever length we like. So we don't actually know where to look in our word to find that V, X, and Y. That V, X, and Y can be anywhere. So let's try to be systematic. Let's start at the start. Well, our VXY could be in here. Our VXY could be partially in here and partially in here. Because notice that because our first number has n bits in it and our second number has n plus 1 bits in it, we could actually steal like a bunch of bits from the end of our first number and a bunch of bits from the start of our second number. Are they called bits when we're in unary? I'm not actually sure. I'll keep calling them bits, and if it makes me look like a fool, well, so be it. Oh, where's my cursor gone? Here it is. Or we could be in here. So our VXY could be found in there. Or our VXY could be found in here. Partially in that second number, partially in that third number. Or our VXY could be found in here. So far we've actually had 5 different cases, but we're not done because we haven't even considered how those dashes get involved. So it could be the case that our V could contain our dash and not contain anything else, and our Y contain nothing. But it also could be the case that our V contains the dash and contains something else, and our Y contains nothing. And it could be the case that our V contains the dash, does contain something else, and our Y contains something. You can think of so many different ways that you could consider how our V, X, and Y might interact with this single dash, which is why it's so important to try to come up with generalizable cases. Now notice that if we were to include our dash as part of either the V or the Y, because what we care about here is the V and the Y, because the V and the Y are what get pumped. So if we were to include this dash as part of our V or our Y, then we wouldn't be able to include this second dash as part of our V or our Y, because to include both of them would mean that our VXY would need to be a length of n plus 1 plus 2, because each of these dashes also take up 2 character slots. And n plus 1 plus 2 is greater than 2 to the k, because as we know 2 to the k is equal to n. And we know that vxy cannot be greater than 2 to the k. So this tells us that we cannot actually have both of our dashes involved in our vxy simultaneously. So we can have a single dash involved. Now, let's think about what happens if we have a single dash involved. Well, if we have just a single dash and we pump upwards, thus creating more single dashes, we'll actually see that we do not have an increasing sequence, because each of these dashes, if they're right next to each other, mean that we have the number 0. So we'd be going from 1 to the n, so we'd be going from the number n to the number 0. And that's not increasing. But remember, you don't get to pick exactly how your vxy interacts with your word. You have to consider all of the ways that your vxy could interact with your word. So this means that you cannot say, well, what if it's just the single dash? There may well be other things that are included in your vxy. So what if what gets pumped is your single dash and maybe some number of ones? Well, what will end up happening is when we pump upwards, we would repeat this. 1, 2, 3, 1, 2, dash, 1, 2, 3, 1, 2, dash, 1, 2, 3. So in this case, we've pumped up to I equals 3. And you can see that because this is our original thing. And then we've pumped it 2 more, whoopsies. We've pumped it 2 more times. So that's when I is equal to 3. Now, in this case, we can see that we still have this issue of our starting number being n, and then we're going to have the number 5, for instance. And presumably, 5 is less than n, although we don't actually know that for sure. Now, to be honest, we don't actually know for sure whether it's possible for us to have exactly 2 bits before our dash and exactly 3 bits after our dash in our pumped part of our word. But what do we know for sure? Well, we know that we cannot have both the dashes. Now, I know that I have said this over and over and over again, but it's so important to drive this home. We know that we can't have both the dashes because of this third rule. Now, another consequence of this third rule is that if we were to max out our pumping, or if we were to max out what part of the word is getting pumped, so if we were to max out our vxy, while including a dash, the largest number of ones that we would be able to include would be what? Well, it would be 1 to the n minus 1. Why is this? Well, it's because our vxy has to be less than or equal to 2 to the k, and we've defined 2 to the k to be equal to n. So that means the length of our vxy can have at most n things in it. That dash counts for one thing, so that means we can have at most 1 n minus 1 remaining things. Why am I driving this home? Well, if we think back to why our pumping failed when we picked that specific number, when we picked that we had 5 bits in addition to our dash, it was because we ended up, when we pumped, creating numbers that came after n that were smaller than n? Well, we can see here that if we include n minus 1 ones as part of what's going to get pumped, in addition to our dash, then when we pump, we'll end up with n ones, followed by a dash, followed by n minus ones, followed by a dash. And then maybe, depending on how many times we pump, we might get a couple of n minus ones. Now, keep in mind, this is if we max it out. So if we pick different values of, if we pick different numbers of ones to include in our VXY when we're pumping, we're still going to end up with a number that is smaller than n. So we don't actually have to consider all of the different ways that we can put our dash into VXY. It's actually enough for us to say, look, if we have a dash in either our V or our Y, then when we pump, we will end up creating a number that is smaller than n, but that comes after our first number. And then you'd have to explain how this is the case, how this happens, but notice that we have been able to generalize that case. So let's write down our first case. Our first case is Vy contains the dash. So really emphasizing this idea that we want to generalize. Now, you could go through and make all of these beautiful different colors their own cases. That would be perfectly acceptable for you to do. So you could talk about how your second case is where Vy contains one or more ones from the first number. And then you could talk about how maybe if we were to pump upwards, then we would end up creating a number bigger than our second number, and thus violate the rules of increasing. But it's not necessary for you to go through and write out each of these pretty colors as their own case. Because notice that with this brighter green, so with this second number, if our Vy contains one or more ones from our second number and we pump upwards, then we'll end up with a number that's bigger than our third number, thus violating the rules of increasing. And notice that if our V is in our first number and our Y is in our second number and we pump upwards, then once again, we're going to end up with numbers that are bigger than our third number. So the logic behind why each of these three cases break when pumped is the same. So given that that is what's going on, you're probably better off saying something like, case 2 is the case where Vy contains ones from the first two numbers. And then you can talk about how when you pump upwards, you make numbers that are bigger, and you'll eventually make a number that is bigger than the third number. This here is good because it is generalizable. It would be really tempting to say something like, let x, no, we don't start with x, we start with u. Let u equal the empty, let v equal 1, let x equal 1 to the n minus 1 dash, let y equal 1, let z equal the remainder of the word. That would be a really tempting case to give, and it would be a terrible case to give. It's far, far, far too specific, because you have only demonstrated one way to break your word up into u, v, x, y, z when you give this case. And remember, there are actually an uncountable number of ways that we need to break our word up, because we don't know what our n could be equal to. So you do not want to go about defining your words with this level, sorry, not your words, defining your cases with this level of specificity, because you will fail to demonstrate that you've considered all ways to break your word up into u, v, x, y, z if you go about it this way. Now, the final case, of course, is case 3. And case 3 is vy contains ones from the last two numbers. And there we'll be able to say, look, if you pump down, actually no, we won't. Because if you pump downwards, it might be possible for you to pump downwards and have your numbers equal your first number. That's interesting. So I haven't actually considered how I would go about doing these cases. So we've already covered that bright green case in the middle. So the interesting thing left to do is that final number. How do we pump that final number downwards? And looking at this, I actually think that we've chosen a bad word. I think that we might want to reconsider our word, and instead of making it n plus 2, let's make it n plus 1. So let's make it equal to the word that came before it. So now we are guaranteed that if we were to take a bit from this word and pump downwards, we would end up with a word that's smaller. We would end up with a number that's smaller than the number that came before. Now, it's really important to consider these edge cases, because that edge case from the previous version of this word that I had, that was exactly one edge case that would fail. So let me just spell out what it would have been. So if we had said u is equal to 1 to the n dash 1 to the n plus 1 dash, v is equal to 1, x is equal to empty, y is equal to empty, and z is equal to the rest of the word. Note that when I pump this v downwards, I would end up with, so in the original version of the word that I had, I would end up with a word that would have been, well, what my words now become. So 1 to the n, 1 to the n plus 1, 1 to the n plus 1. And in increasing, we don't demand strictly increasing, and so this isn't actually a problem. So if we want to make this so that we can actually pump downwards and create something that breaks the rules of the language, we need to actually change our word. So we change our word, we make it n plus 1. And what happens now? Is that going to be enough? Because now consider what's represented with the red line. So with the red line, we're grabbing a 1 from, we could hypothetically grab a single 1 from this number and a single 1 from this number. And we can pump those up to our heart's content and still have an increasing sequence. So we're relying on being able to break this by pumping downwards. But when we pump downwards, if we take exactly 1, 1 from each of these numbers, we will end up with the sequence 1n, 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 which is perfectly legal. So, once again, we might actually want to change our word. Now, you might be tempted to think that we can change our word by getting rid of these plus ones. But that will actually break the logic of this case. Because remember the idea with this case. Oh, will it break the logic with this case? No, the logic with this case will remain. I got ahead of myself. So I think that is an improvement. I think that is the best possible word for us to use if we want to prove that increasing is not a context-free language. We've gone through all of our cases. So we've said case 1, vy contains just the dash. Case 2, v1 contains ones from the first two numbers. And case 3 is v1 contains ones from the last two numbers. And we've had a quick chat about how we would show that these cases fail. So, this has been a video talking about the ways in which you can go about designing cases when writing a pumping lemma proof. The main takeaways that I'd like you to have is, well, actually it's just really one main takeaway. You want your cases to be sufficiently generalizable that you have indeed covered all the possible ways of breaking your word up into its relevant sections. A good way to ensure that you have actually gone through all the ways of breaking your word up is to do what I've done here and just work your way through the word in a linear fashion. And then once you've done that, come back and see which cases can be consolidated together. All right. I'm going to stop talking and I'm going to end this video.